In this lecture, we're going to cover wave-particle duality. So we've already seen wave-particle duality for light. We'll briefly recap on that here, and then we'll spend most of the time talking about wave-particle duality for matter. In particular, we're talking about the deBroglie wavelength. When is wave-like behavior for matter apparent? Because of course we think of matter typically as having particle-like behavior. And then some connections between the wave-particle duality and the Bohr model. So, as mentioned before, we've already talked a lot about wave-particle duality for light. We see the wave-like behavior of light in phenomena such as reflection, refraction, diffraction, constructive and destructive interference, and so on. But we also see the particle-like behavior of light, where light delivers energy in packets, which we call photons. This is apparent in things like the photoelectric effect, in the atomic line spectra that we discussed in the last lecture, and many other areas of chemistry. Just to give one more interesting example is vision. So inside the rods and cones of your eyes are these key cis retinol molecules. And however, when these absorb light in the form of a photon, it can cause an isomerization about this bond to go from the so-called cis form, where these two bonds are on the same side, to the trans form, where they're now on the opposite side. And that's, as I said, a key feature in the detection of light by our eyes. And this is caused by the excitation of the molecule from a ground to an excited state, which can then relax into the trans retinol form. So given that light has this wave-particle duality, what if matter has the same thing? We tend to think of matter, baseballs, rocks, all those things, as being very particle-like. But what if they also had wave-like behaviors? And so deBroglie proposed this as a graduate student in the 1920s. And so in particular, he proposed this expression for the wavelength of an object. He said that the wavelength is going to equal Planck's constant divided by its momentum, which is mass times velocity. Now this seems pretty out of left field, but you can actually motivate this with a really simple argument. He started off with the mass-energy relationship from Einstein's famous formula, E equals mc squared. And we also know that the energy of a photon is E equals hc over lambda, which is just the other form of E equals h nu. And then we can set these two things equal, solve for lambda, and we get lambda equals h over mc, where c again is the speed of light. But of course, physical objects aren't moving at the speed of light, so if we replace the speed of light with whatever velocity they're moving at, v, we get this expression for the deBroglie wavelength, lambda equals h over mv. Now, does this even make any sense? And if so, does it even matter? I mean, for example, you've never noticed any wave-like behaviors of rocks, or the chairs you're sitting in, or anything like that. So let's take a little bit of a closer look at this. So why don't we compute the deBroglie wavelength for a baseball that's been thrown at 90 miles an hour? So the mass of that baseball is going to be 0.14 kilograms. The speed at 90 miles an hour translates to something like 40 meters per second. We have Planck's constant. A joule is 1 kilogram meter squared per second squared, so we can go ahead and compute the deBroglie wavelength. So lambda equals h over mv. I'm going to plug everything in. If you use this way of disentangling the joule into the fundamental SI units of kilograms, meters, and seconds, you'll see that all the units cancel properly and we end up with a wavelength of 1.2 times 10 to the minus 34 meters, which is tiny, right? That typical size of an atom is on the order of 10 to the minus 10 meters. That's similar to the length of a chemical bond as well. And so this is something like 24 orders of magnitude smaller than an atom or a basic chemical bond. So this is far, far too small to ever observe in any sort of scenario. So macroscopic objects, if they have wave-like behaviors, the wavelengths of those objects are far too small for us to ever detect. Let's try an example. Go ahead and try to compute the deBroglie wavelength for an electron that's moving at 1% the speed of light. Here again is the expression for the deBroglie wavelength. Here are some helpful constants, and here are some potential answers. Go ahead, pause the video, attempt this problem, and then hit resume when you're ready to see the solution. Okay, so to solve this problem, what we're going to do is we first need to figure out what's the speed of this particle. The speed of light is 2.998 times 10 to the 8th meters per second. If we're moving at 1% of that, we're moving at 0.01 times the speed of light, which is 2.998 times 10 to the 6th meters per second. We have the mass of our electron, we have its speed, we know Planck's constant, so now we can plug in everything and compute the wavelength. When we do that, again, our units all cancel nicely, and we find that the wavelength is 2.43 times 10 to the minus 10 meters, or answer B. So the interesting thing here, though, is that this wavelength, in contrast to our baseball where the wavelength was so tiny that we'd never observe it, this wavelength is still very small, but it's on the scale of an atom. It's about 2.4 angstroms. This is sort of on the size of a typical chemical bond. It's about double a typical carbon-carbon chemical bond. And so this is now a wavelength that maybe is going to have some relevance when we talk about objects on the atomic scale. And so in other words, the wave-like behavior of matter is something that's not important in the macroscopic world we live in, but it is something that becomes much more important as you get to smaller and smaller objects. So in the macroscopic objects like basketballs and all the things we experience in our day-to-day lives, the wavelengths are far too short to be detected. So we only ever see the particle-like behaviors of these objects. But as you shrink down to the scale of proteins, molecules, and atoms, these things get smaller and smaller, and the wavelengths get increasingly important relative to the dimension of the objects, particularly for molecules and atoms. And so in this regime, we have both the wave-like and particle-like behaviors being very important. And so this is where the wave-particle duality becomes essential to understanding the nature of matter. Now all of this might still seem a little far-fetched, but we can show direct experimental evidence of this wave-like behavior of electrons. And so to see this, let's first talk briefly about X-ray diffraction. So X-ray diffraction is a strategy that's widely used to determine the structure of crystals, and from that you can often get the structures of molecules and so on. And so the idea is that when atoms or molecules are in a crystal, they're packed with certain packing densities, and there are going to be gaps between those atoms and molecules and the layers of atoms and molecules and so on. And so if we shoot the correct wavelengths of light, wavelengths that are commensurate with the spacing between these layers, we can potentially diffract those wavelengths of light off the crystal, measure a diffraction pattern, and then determine the structure. So you get diffraction patterns that look like this, where each of these little dots is coming from the diffraction of the X-rays in a crystal. And so this is a very wave-like behavior of the X-rays. It turns out that you can do the same thing with electrons, because like X-rays, the wavelengths, the deBroglie wavelengths of electrons, are commensurate with the spacings in the crystal. And so just like we can diffract the X-rays off the crystal, we can diffract electrons off a crystal. And so you get patterns like this. And again, from these patterns, you can back out the structure. So this is a clear manifestation of the wave-like behavior of electrons, which are particles that we would normally not think of as having wave-like properties, but here's direct experimental evidence that they do. Finally, let's revisit the Bohr model in the context of the deBroglie wavelength. So the Bohr model made this assumption about quantized states. Remember, we had that the angular momentum was quantized as one of the key assumptions in the Bohr model. But that didn't really have a firm justification. The primary justification then was that it worked. But what if those key states are the only ones where the deBroglie wavelength can fit complete wavelengths of the electron around the orbit? And so in particular, suppose this is my orbit with some radius and circumference associated with it in the dotted line. If my wavelength is of this particular wavelength here, I can fit 1, 2, 3, 4, 5, 6 complete wavelengths around this radius in this picture. And so if you think of the electron as having circular standing waves, and that the orbital circumference must just be an integer multiple of the wavelength, then you get an expression like this, where 2 pi r, the circumference of our orbit, is equal to some integer n times the wavelength, where n is 1, 2, 3, etc. And from this expression, you can actually derive Bohr's quantization of angular momentum. And so you can get a little more justification for this assumption that Bohr made from this idea of the deBroglie wavelength. Now, this still doesn't solve all the problems with Bohr's model. It doesn't solve the problem, for example, that it doesn't work for any atom with 2 electrons or more, but at least gives us a little better sense of what might be lying beneath the surface of the Bohr model, and perhaps a little more about why the Bohr model works. So to wrap up, we've reiterated how light can exhibit both wave-like and particle-like behaviors. We then talked about the deBroglie wavelength as a way of describing wave-like behavior for matter. We saw this wave-like behavior only becomes apparent in microscopic objects, things on the sizes of atoms and molecules, but you can observe this experimentally. This is a real phenomenon. However strange it may seem, particles do exhibit wave-like behavior. However, right now the deBroglie wavelength is still just another somewhat ad hoc solution. We want a theory that's more universal, more general, and that's going to provide a framework in which we can truly describe all of chemistry. And for that, we're going to need something called quantum mechanics, which we'll talk about in the next lecture.